So for part 2 here, we're going to talk about a couple of other things regarding functions. And the first one we talk about is this property of continuity. Okay. Some functions are going to be continuous, some are not. Okay. In this particular case, we have a fourth degree function, which we'll talk about later. But ultimately, when we look at the graph of this, keeping in mind that we can assume that the graph has arrows and it's going to continue in that same manner forever, both directions. Okay, we consider this one what we call continuous. Okay, there are no breaks or anything going on in here, and that would make it not continuous, kind of like this one that we have over on the right. If we have any kind of graph that has a hole in it, okay, then we call that a discontinuity. In fact, it's what we call a removable discontinuity. So any graph that we see that has a hole in it, okay, whether there's a point defined above or below that spot or not, okay, we still consider that a removable discontinuity. And for today, all we're concerned about is looking at the graphs. Okay, we'll talk about the algebra part of this later. Okay, again, we're looking at this from a graphing standpoint. Okay, we'll look at it from an algebra standpoint later. Okay, and notice this is another removable discontinuity. Notice this one has a hole in it, but it doesn't have a point above or below it. Okay, this one had a hole and a point above it. Could have been below it. Okay, this one just has a hole and no point. Okay. Both of these are considered removable discontinuities. And again, we'll discuss later why they call it that. But for now, okay, we'll just know that the graph of it is what we need to identify. Okay, sometimes we have a graph of a function that might be defined by two different functions. Okay, and there might be at certain points, there might be what we call a jump discontinuity. Okay, and now one thing I want you to notice that there's an open circle and a closed circle. If this had been a closed circle also, then this wouldn't even have been a function anymore, would it? Okay. So if there's a jump and it's a function, okay, one of these has to be open, one of them has to be closed. Or they could both be open. And that would still qualify as a function. So this is what we call a jump discontinuity. And then finally, if there's an asymptote, okay, keep in mind that this is implied when you see this on your calculator that there's an asymptote here. Okay, we call that an infinite discontinuity. Okay. So if we go back to the example that we used in the first part and look at our graph of y equals 2 over x, okay, we can see that this is not a continuous function because at 0 we have what type? It's an infinite discontinuity. It's an asymptote, isn't it? Okay. So the type of discontinuity is infinite, and what does that produce on the graph? It produces an asymptote. Okay. All right. Well, let's take a look at just a couple more pictures here. And this one says, which of the following figures shows functions that are discontinuous at x equals 2? Well, if we look at x equals 2 here, do we see any of those discontinuities in this graph? No. So this one is continuous. What about here at 2? What do we notice here? Yeah, there's a hole in the graph, so therefore this one is discontinuous at 2. And what type? If we had to tell what type, that would be a removable. We don't say it's a hole because again, we're talking about types of discontinuities, and there were only 3 that I gave you. Okay, one was removable, one was jump, and one was infinite. So if it says what type of discontinuity, then only those words can be your 3 answers. So this would be a removable discontinuity, but we could also say for the graph it would produce a hole. Okay, so that would be removable. Okay. And then the last part that we're going to talk about for today is this idea of whether a function is increasing or decreasing. Okay. And in the case of the one on the left here, on the top left, this would be called an increasing function because as we move from left to right, the values of y are getting what? They're getting bigger. This one is a decreasing function because as we go from left to right, the values are getting smaller. Okay. If we had a horizontal line, this would be a constant function because it does not increase or decrease, it stays constant. Okay. And then we have some functions that could have different parts to them. Okay, in this particular case, we would say this one is decreasing negative infinity to negative 2. Okay, and notice the interval notation. Okay. It's constant from negative 2 over 2. Okay. And I want you to notice that on 2, from 2 to infinity, it's increasing. Okay, a main part of this is that these are x values. when we give an interval of increasing or decreasing or constant, okay, we're describing what x values this function is increasing on. Okay, has nothing to do with the y coordinates. Okay, we're just saying that on the coordinate plane, if we look at the x-axis here, from negative infinity until we get to negative 2, here's negative infinity way over here, until we get to negative 2, what's going on with this function? It's what? It's decreasing. As we go from negative 2 over to 2, it's not decreasing anymore, now it's constant. And as we go away to the right from 2 all the way to infinity, this function is increasing. So you notice that we list them kind of like a domain, don't we? Okay, and that's exactly what they are, is they're x coordinates. And so on these x coordinates, the function is decreasing, constant, increasing, etc. All right. And what I want to look at finally is this function, which is got an interesting definition here. You notice it's an absolute value function, but it's an absolute value minus an absolute value. If we were to graph that, let's take a look and see what we'd get. If we do our math, num absolute value, x plus 3 minus absolute value of x minus 2. We would see that graph, okay, which looks to be essentially 3 distinct line parts. We got a horizontal line, we got a line with a slope, and then we got another horizontal line. Okay. And they've made this function into a definition, okay, that we call a piecewise definition. Okay. So this is a piecewise definition for this function. Okay, and what we're saying is that this function, it looks like the line y equals negative 5 when x is less than negative 3. So notice at the point negative 3, that's when it turns into the other line, the middle line, if you will. But before that and off to the left, it's just the line y equals negative 5. It's horizontal. Okay, it's the line y equals 5 when we're anywhere greater than 2. Okay, and then between negative 3 and 2, okay, it's the line 2x plus 1. If we were to take these 2 points and calculate the slope, we would get 2. And notice that if we zoomed in on this, it would cross the y-axis at 1. Okay, so this is the regular definition on the left. Okay, this would be the piecewise definition. Anytime we have a function like that that's made up of 2 or 3 different parts like that, okay, we call that a piecewise function. Okay, and if we analyze each piece separately, okay, we can answer questions like this, which is identify the intervals on which f of x is increasing, decreasing, and constant. Okay, so looking at our picture, either from our graphing calculator, or I have a picture of it here also. Okay, what would we say about this branch down here? Okay, this branch would be increasing, decreasing, or constant. Yeah, this is constant. So it would be constant on negative infinity till negative 3. And then wouldn't it be constant again from 2 to infinity? Okay, so you'll notice that the graph suggests that it's going to be constant from here to here. And they made a huge mistake on here. Anybody see the huge mistake? Yeah, definitely not an and here. Okay, and would indicate that there's some overlap of those two, and there's certainly not. What should be between those two? An or, if you use words, or we would write it as negative infinity to negative 3 union 2 to infinity. So that would be the proper way to list it. Okay. All right, and then also between those 2 points, okay, we're increasing. We can see it's going up as we go from left to right. So we'd say we're increasing on negative 3 to 2. Okay, and that's a description of the interval on which this function is increasing. Okay. Questions? Okay, so that said,